Hello and welcome to Programming Like It's 1979. This is our lab on RAM and computer memory. So this week we're going to be building some memory chips. If you have missed the first part of this series, please click the card to watch that and some of the earlier ones first. We are using the book Neeson and Schocken, The Elements of Computing Systems. We're going to begin with our bit component. We can see the specification here. It has two inputs, an in and a load, and one output and an out. So let's take a look here at our diagram. I've added another input here, which is the clock input, which is implicit in any of these memory-related things. So we're going to grab a D flip-flop here. You can see it as an input for the clock, so I'm going to drop it right there. So you might think, well, let's just route the input of our bit into the D flip-flop. The problem with that is that the specification of the D flip-flop says that if load is 1, then out at time plus 1 equals in at time. Otherwise, out doesn't change. So our D flip-flop has the delay for one cycle behavior that we described in the lecture, but it won't give us this and won't change behavior. So it's really that and won't change that we care about. So what do? Well, we see in the specification, the very first word is the magic word. The magic word is not please, the magic word is if. So let's look, what do we do when we have an if? Well, we think of a multiplexer. So let's grab a multiplexer and put it right here. You could see I was prepared. I actually put the inputs in the correct place here. Load is going to be the selector for our multiplexer. When load is true, we're going to use our second input. That's going to be in. And so then the only remaining mystery here is what is the first input to the multiplexer? Well, I'll tell you the output of the multiplexer goes there. The answer is this is a feedback loop. We take our output, which is going to the output of our bit, but then we also loop it around right into the first input of our mux. That's it. Let's actually run it, make sure it works. So everything, by clicking here, I can advance the clock cycle, so I'm going to go ahead and do that. You can see nothing is changing. If I change the input to true and advance the clock, again, nothing changes because the load bit is not set. If I set the load bit, nothing changes until I advance the clock a full cycle. Now we have a high output. If I unset that load bit and unset the input, or rather set it to 0, I can advance the clock as much as I want. That value is not going to change because it is looping back around. That's our bit. In many of the weeks that we do NAND Tetris, we find that the hardest challenges are further along in the more you do the project, you get to the tougher projects later. This week is actually the exception because although this is a very simple diagram, conceptually, until you get that realization that you have this selection to do to decide what to feed into the DFF, that's actually the hardest. Everything else here that we'll do this week, we're not even going to diagram it because it's all just going to be copying, pasting RAM into bigger and bigger banks of memory and understanding how to select between them. Let's actually write the HDL to go along with this diagram. Okay, we only have two components here. We've got a MUX and we've got a DFF. Right off the bat, we know the DFF is connected to out. We also know that we'll need another wire coming out of that output. We know that DFF's input is coming from the MUX. That tells us what we can call this. We know the selector is our load input. I think I said the second input is the input. And then here's our loop back where DFF out is running back to the beginning, to the first input of the MUX. That's it. It's that simple. That's our bit of memory. Let's try it in the simulator. Okay, we've loaded that HDL. We're going to load our test file, crank that up, run, and there's actually quite a few tests here, something like over 100 tests, I guess making sure lots of time passes so we don't forget the value. And that's our bit. And so we have created computer memory. We've created some RAM. Next, let's move on to our register. So the register looks just like the bit, except it's an array of 16 pieces of memory instead of a single one. So I am not going to draw 16 of these. I'm not even going to do an example. I'm just going to do this in HDL. I hope you don't mind. So clearly, the naive approach, I think, is the best one here. We're just going to take 16 of these bits. Here we are. So before we copy and paste these, what are they going to look like? Well, every bit is going to be hooked up to our single load bit, and it's going to be hooked up to the same load bit. It's all of these that are going to be using the bus syntax. So the 0th bit will be hooked up to in 0 and out 0. The first bit, or the next bit, will be hooked up to in 1, out 1, and so on to the 16th bit. So let's go ahead and do some copy pasting. I'm sure Visual Studio Code has some macro to actually do this for me, but I'm too lazy to look it up. Laziness is a programmer's greatest attribute, actually. A lot of the things that I've learned in my life, I've learned because I was so lazy that I wanted the computer to do it for me. But I guess I should say I'm not lazy enough to figure out how to get Visual Studio to auto-number these for me. If you know how to make Visual Studio auto-number these for me, please say so in the comments. I will do it. No, I never make any typos at all. In fact, that's why I'm such a good programmer, is the fact that I type so well. Really, I was just born with an innate ability to never make syntax errors. All right, now after no effort at all and really no mistakes and no typos, no having to go back and fix numbering, really it was like that. It was super easy. Now we have a register. So let's go straight to our hardware simulator, load that register in, and load our test and see how it does. I expect this one to work. I'll be surprised if this fails. And we have now created a register. So I hope you could see that took longer to do than the bit because of all the copying and pasting, but conceptually it was actually so simple anyone could do it, including you, including me. Let's take a look at our program counter. Make a little more room here so we can actually read the comments. So this is a 16-bit counter, and we can see this has a fairly complex description here. Each individual behavior is very simple, right? If nothing happens, then it's going to hold on to the value. Otherwise, there are 3 flags: load, inc, and reset. Reset's going to set it to 0. Load is going to set it to whatever in is. And inc is going to increment it. Integer addition. Thank you for specifying that. So we're going to need a few pieces here, right? We know we're going to need a register. We know that register is going to be going there to the out bit. We know we're going to need a number of muxes. So we see if here. If's the magic word, but here we have this kind of nested structure of if-elses. So how are we going to simulate that? And what's the kind of hierarchy that's going to get us these disjunctive behaviors? If one of these behaviors happens, then the other one doesn't. Of course, you might recall from some of our earlier exercises from our last chapter with the ALU very often the correct way to handle these things in circuits is to always calculate all the values, and then you choose the one you need. So I think we're going to do that. So since we know we're going to need an incrementer, we're going to drop an INC16 chip here. And we're going to go ahead and just name these wires as we go. Inc out. Okay, that sounds good. And let's go ahead and, I don't usually name the in wires, but I'm going to do it. We're going to try and keep track of these this way. So we know there is an if that is going to feed this incrementer. So I'm going to say that's a mux. It's got to be a mux. And I'm going to declare that it's this mux, which is meaningless now because we don't actually have an ordering for these. But I'm kind of declaring that this is, you know, the inc mux. And it has a selector, and its selector is this inc input. Great. So what are its A's and B's going to be? Well, its A input, what it does if this is not set, has to be just whatever's coming out of the chip. So I need another wire here to give a name to this, and let's call this register out. And reg out is going to be this here. And then the B has to be, I've already made a mistake. The B has to be inc out. This was a dumb mistake, so we'll call this inc mux out. Right? Yes. So now we have to start thinking about hierarchy. So in this if statement, the reset is actually the most important thing. The reset is the mux that is closest to the register. Because if reset is true, then it doesn't matter what load and inc are set to. We're going to throw them away. Right? Or conceptually, I guess you could say, we're going to load them, but then we're immediately going to reset them. So let's do this reset mux next. We need a chip. We need it to be indented correctly. A, again, is going to be reg out. B is going to be a constant false. So this is a 16-bit. Oh, this needs to be a 16-bit mux, doesn't it? Oops. I think I could just do that, and that should work. So then B, 0 through 15, is going to be equal to false. That's a binary 0. Selector is reset. Out is reset out. Okay. So I just said that reset is the mux closest to the register. So that implies that reset out is going into the register. Oh, I remember this. Okay. Yes. So you might think now, what is this load going to be? Right? You might say, well, obviously, this load is going to be this load input here. But is it? I don't know. I think we're going to come back to that. Spoiler, it's not going to be. We'll just put those question marks there and make it a Scooby-Doo mystery that we're going to deal with later. Okay, so let's work out. We've done the innermost mux here, and we've done actually the outermost mux here. So there's actually one between these two. 16. And that's going to be our actual load mux. So again, the 0, the first input to the mux is going to be our reg out. And this looks very much like just our normal RAM, right? Our first input, our second input is going to be our input to the chip, our in. Our selector this time is going to be this load. And we'll call this load mux out. I'm going to call this reset mux out. Change it over here. So these three muxes are all wired up to the output of this register. They all propagate or preserve propagate or preserve that previous value if the selector is not true. And is that correct? I don't think that's actually correct. So what I've done here is wrong because let's say the ink mux is true, the ink selector is true, and the others are false. We go into the ink selector, which is kind of our outermost selector, right? And it's true, so we increment it. And then we're going to get to kind of the next mux in the series, which is this load mux. But right here, we're kind of throwing out this value completely. And so I think we really do need to kind of wire these in series, kind of viewing this as the outermost and reset as the innermost. So I think something like this conceptually works. And now these three are all going to get a bite at the apple, so to speak. The input is vectored here. And so then we return back to this load bit. And my answer is that these three muxes by themselves create more or less a complete array of possible truth values. So whatever they're doing, that's the answer. And that's true even in the case where they're doing nothing, because they implicitly get this value here. And so load is always true. On the register level, that load is always true. The register is never going to make a decision. It's always going to load the value. And just that value might happen to be the value that it held previously. All right. This was a lot of typing with no diagramming. I have no idea. Is this good YouTube? Is this terrible YouTube? I don't know. I probably could have diagrammed this one, but I felt like trying to walk through it just in code. This is actually how I approach problems that are small enough in code to fit in my brain. I don't sit down and draw everything. I do think through them in code. So if this is unhelpful, I'd love it if you told me that. If, on the other hand, seeing me do this type of reasoning out loud is helpful, please leave a comment. I could use the feedback. All right, we're going to save this. This could be a disaster. Let's actually load this in. All right, let's load the chip, PC. Sure enough, we made a mistake. Ink in has no source pin. Right, we did not define ink in. I think ink in is actually reg out. Is that right? I think it is. All right, let's see what other mistakes we made. Load it again. This time it did load. This could be bad, man. This might not work. Oh, I cannot believe that worked. I mean, the outcome was never in doubt. Of course, my perfect code would always work on the first test run. I have actually a very superstitious belief that if I write a substantial amount of code and run it through the compiler and it compiles with no syntax error the first time, I'm really scared, because that means that whatever mistake I made was super subtle and is going to be hard to fix, as opposed to a syntax error like this, which is fairly easy to fix. Mistakes, folks, we all make them. Don't be ashamed of them. Revel in them and learn from them. Moving on, let's look at our RAM chip, RAM 8. Memory of 8 registers, each 16-bit wide. Out holds the value stored at the memory location specified by address. If load is 1, then the in value is loaded into memory, specified by address. The loaded value will be emitted to out from the next time step onward. All right. So right off the bat, we know we need 8 registers. It tells us point blank, there's 8 registers. I'm actually not sure what we're going to do here. Let's go ahead and put our registers down and see if that makes us feel a certain way. Out holds the values stored at the memory location specified by address or address. So we actually have 2 decisions to make here. Probably more than that, but at least 2. One decision is, where does this in value go? The other is, which register does the out value come from? So where does something go and where does something come from? So right off the bat, I'm thinking that there's both a mux and a demux happening here. A mux is about selection from a number of alternatives, and a demux is about, I always think of it as like routing. You have one value coming in, and then it needs to go to one of, in this case, 8 places. So the value that needs to go to one of 8 places is either this input or another value that I'm pretty sure that I know what we're going to do here. The out value, the mux behavior, is actually that all of these outs are potential inputs to our mux, but only one of them goes out the other end, right? So there are 8 of these, so our mux and demux are clearly going to be our 8-way versions. And we know we want to send a 16-bit value out. So that has to be a mux 8-way 16. All right, let's name our registers here. So we'll just call them mem A through mem, was it H, B, mem G, and mem H. And then we're going to pop those over here as the inputs to our mux. Oh, look at that. And because I chose letters, they will match up nicely with the input names, which is always helpful. All right. Our selector is a 3-bit selector named address. And I believe this selector in the 8-way mux is also a 3-bit selector. So I think we can just do that. And that should work. And then this is wired up to out. That's what that looks like. That's the outside of this chip, the out part of this chip. What does the in part of this chip look like? Well, we have these 3 demuxes that we've made. One of them is an 8-way demux. Let's go ahead and define that. And now this gave me a little trouble. I actually remember doing this exercise the first time. And I was convinced that I wanted to route this value, this 16-bit in value, to one of these registers. And I was so convinced that I went down the rabbit hole of making a demux 8-way 16. I thought that would be helpful because then I could route this entire value. But really, this is Nielsen and Schuck and giving you a hint, because these registers will hold their own value, the old value, as long as this load bit isn't set. And so the subtlety here, and if you got tripped up by it, I feel you. I spent I want to say an hour and a half kind of staring at this and tearing my hair out the first time I did the class. You don't do that. The thing that we're going to route is actually the load bit, not the input. The input is going to, I don't want your autocomplete. The input is just going to be routed there no matter what. And it will simply be ignored if the load bit is not set. So our selector is once again the address. We'll call this DA, DB, etc. Let's cut to the chase. All right, so this is our kind of memory bank. And I almost wish I had drawn this one. It just would have been a nest of wires, which is why I didn't. But if you could kind of squint at it, you've got this central bank of memory. And then on either side of the memory, you have this complex of a demux and a mux that are routing values in and out of it. It's has a very distinctive look. If you actually look at a chip, you could actually usually identify where this is going on. And there is a game, a programming game called Silicon Zeros, in which making registers, making use of registers and addressing them is done in a really neat visual way. And maybe I'll grab some gameplay footage and splice it in right here just to show you what it looks like. Because once you see that, that really gives you a nice visual intuition about what's going on here. Let's test this and see if I got it right or if I made some mistakes. It's the RAM 8. I did make some mistakes. Let's see, DH. Oh, I put a capital D there instead of a lowercase d. See, every time I make a mistake, I'm going to leave it in here. Load the script, RAM 8. You can see memory mutating over here on the internal pins and on the output pins. And we've done it. We have made a memory bank. RAM 64. Memory of 64 registers, each 16-bit wide. One out holds the value stored at yada, 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 yada. Sounds almost exactly the same as what we did for RAM 8. And already I can hear you thinking, because part of me is thinking it too, oh my Lord, am I going to have to copy paste 64 lines of code? Of course not. We're going to use computers to make this easier for us. And what we're going to do is we're going to note that 64 divided by 8 is 8, which sounds a lot like what we were just doing. And in fact, I'm so confident that this is similar that I'm just going to literally copy paste our code from before and put it here and use it as a starting point to talk about it. All right. I need a little more space. Let me get rid of that. So what's the same and what's different? Same input, we have a load bit, same output. However, our address input is 6 bits. So what we're going to do here is we're going to replace our registers with RAM 8s. The RAMs we literally just made. I'm just copying the first one here just so I can get the... So I'm leaving address as question marks because that's the subtle bit that's going on here. Everything else is going to be the same. So that means I can copy paste this. Does the word register appear anywhere? I don't think it does. I can literally search and replace register with RAM 8, hopefully. Okay. And then, so what are we going to do with this? Well, what we can do is we know that our address field has 6 bits. We know that these RAM 8s have an address field that takes 3 bits. So what we can do is pass the least significant bits on to these RAM 8s. I think we can do that like so. 4 through 6. No, that's not right because they're 0 indexed. 3 through 5. So where are we making the decision for the most significant bits? Well, that's the most significant bit is going to decide, bits are going to decide which of these RAM 8s we address, and then the least significant bits are going to sub-select within that RAM 8. So I think our selector is bits 0 through 2, and that's going to be true for our demux, and it's also going to be true for our mux. And then this simply becomes the thing that we put here, pass on to all of our sub-RAMs. I think that's it. I'm sure I'm going to get some sort of HDL syntax error because some subtlety of addressing this bus, but let's try it. RAM 64, loaded. I'm shocked. So far, so good. All right. We've made a larger memory bank. Not to shock you, the rest of these projects is more of the same. We're going to take our RAM 64 and build that up into larger and larger memory banks. Okay, lightning round. Let's see if we can build these larger structures as quickly as possible. I'm just going to literally put them on screen to prove to you that the logic is exactly the same. The only question is how you handle these address bits. So next up is 512. Again, I'm going to copy paste the code from before. We're going to search and replace RAM 8 with RAM 64. We're going to build a 512. We're going to build our 512 byte RAMs out of 64-bit RAMs. Our address bits, actually, I think these are exactly the same because we're just taking the first 3 bits once again, and then we're going to pass on the rest of the bits. So this is 3 through 8 rather than 3 through 5. I can search and replace that. 3 through 8. That's it. That's the whole thing. Let's test it. Oh, we get a fancier display here now. See different memory banks updating. RAM 512, done. Next, copy everything. 512 times 8 is 4096. We're going to do RAM 4K next. Again, we're just going to leave our copy paste panel up because we're going to need it. RAM 512. Our address, instead of 3 through 8, we're going to be moving 3 through 11. That's it. Let's test it. 4K RAM, done. Let's do the next one. The last one is 16 kilobytes of RAM. Copy everything, paste it. The logic here is the same no matter how big we want to make this. Would actual RAM be built in this many kind of tiers? Maybe not. Depends on probably the efficiency of it. All right. RAM 512 replaced with RAM 4K. And address is 3 through 11. Yes, 3 through 13. And there only need to be 4 of them because 4 times 4 is 16, right? So this one is not exactly the same. It looks like I lied to you. So instead of our demux 8-way, we're going to do a demux 4-way, right? I can do that. Address is just 0 through 1. And we just get rid of these 4 things here. And then mux 4-way 16. Similar logic. 0 through 1, and this gets 2 through 13, right? 3 through 13, 2 through 13. Since this one is different, it's possible that I made a mistake, so we'll watch the tests with interest. Looks like it seems to be working. There we go. Great. That is all of our 16K RAM, and that is the last assignment for this week of the class. So I know this one, in my opinion, this is one of the most ponderous ones to do. It's a little less interesting than many of the other assignments because it is so kind of mechanical. It is a necessary precursor. I think it does a good job of showing exactly how high you can start building this tower. The number of NAND chips we're using for these 16K RAMs is gargantuan. So I think that next week's project, we're going to build the CPU. And that, to me, is the most interesting bit of the hardware that we've been working on. All that we've done so far has been, in my mind, just a precursor to building the CPU, which is the fun part. So I look forward to seeing you at next week's lecture. Thanks for joining me. This has been Programming Like It's 1979. Thanks for watching.